Boom. Hello and welcome back to differential equations. Section 1.3, slope fields and solution curves. Vast majority of you already took Calculus 3. You know what slope fields are. We are going to obviously do that from scratch, but majority of you should know what it is. We're also going to talk about solution curves, and solution curves are actually graphs of your answer graphed on the coordinate plane. We hopefully remember from Calculus 1 that the derivative is the slope of the tangent line. And if you have the slope of the tangent line as a number, that's the value of the derivative, right? When you're talking about a slope field, it is going to be a collection of infinitely many of these little line segments which guide solutions through the space, right? Through that field. When you are trying to understand how these things, well, you've seen the images, right? But and we'll actually obtain them by hand because it's not nuclear science. It's actually very easy to draw those. But, well, even if it's nuclear science, sit down and learn it. But the key thing here is to understand that this is going to be a graphical way to solve the equation. Many of you, I would believe, missed in your previous education that every equation can be solved graphically. I teach that when I teach my classes, but again, not everyone took my classes. And I especially emphasize this in intermediate algebra. I emphasize in pre-calculus 1, and then whenever is necessary in calculus. So before I go to slope field, where we have a 2D, well, this 2D as well. When we have a function to be solution, let's go and talk about a very simple case of x plus 3 equals 5 equation. So this equation is something you learned, the first equation you learned how to solve, and you learned to solve it by subtracting 3 on both sides. But the alternative approach to solving this equation is to actually graph the functions that you see on the left and right of equal sign and look for their intersection. These two functions will intersect at x equals 2, which is the solution. So now if you carefully graph this using the square paper, which you all have, luckily, the left equation is the 45-degree line through 3 because the slope is 1. And the right-hand equation is the horizontal line through 5. And as you can see, they are intersecting at the point 2, 5, where x is equal to 2, which is the solution of the equation. So now, what is this business of minus 3 on both sides? How do you represent that graphically? What happens when I subtract 3 on both sides? I immediately get x equals to 2. But look at the graph, right, of x equals to 2. First of all, right, x equals to 2 is the vertical line that goes through 2. And there's nothing else to think about, nothing else to talk about. This is where the new function cuts through, well, x equals 2 is not a function because it fails vertical line test, but the graph cuts through x-axis. What is important for you to realize, and you realize this maybe in pre-calc 1, depending on how it's taught, you realize that there are equations that cannot be solved by these means of algebraic manipulation. You have an equation that says 3x equals e to the x. You can just cry here, because there is no way to isolate x. If I decide to free up x on E by applying ln to both sides, I will free up the x on the right-hand side, but I will bury under ln the x on the other side. There is no way, comma, in hell, comma, to solve this algebraically. The way you solve these equations is graphing, Newton's method, numerical methods, and so on. So you will be, to solve equation 3x equals e to the x, you will draw e to the x, you will draw 3x whichever way it cuts, and then they intersect somewhere. And that intersection, which will most likely be an irrational number or something, will be the solution. It cannot be solved algebraically. So we are going to understand now that the graphical solution to equations is the most powerful, tedious, but most powerful way to solve. Because remember, the first equation, I can solve it by -3 both sides, right? The second equation, I cannot. Both of them can be solved using graphical method. So graphical method is the one that solves all problems. But for convenience, we learn how to deal with quadratic formula, how to deal with conversion for e to the x, ln x, and so on. Now we are going to hop into the world of higher order equations, which is differential equations. So now you are no longer looking for a point on x-axis where you have x-intercept, which is called the solution or the root or whatever. You are now looking for the entire function. And those functions wiggle their way through the xy coordinate plane. Sine function, e to the x function, whatever other function you might think of. So we need to find a mechanism. Like the earlier goal was to make the functions intersect, and that's the... Oh, by the way, the function has no solution. The intersection doesn't happen. That's another thing, right? So if you have an equation and you graph it and the two graphs don't cross at all, then it's no solution. So now that we are jumping into the differential equations world, we need to make this slope field, which would be like a guide for these graphs to snake through it, and they have to follow the way the field bends. Immense application of this stuff. For instance, your LCD screens are made out of liquid LCD, like liquid crystal display. These liquid crystals are very interesting creatures. They're all over the place, right? You introduce magnetic field and they start arranging. And the way they arrange is by magnetic fields, right? The way they arrange, they give different colors and so on. It's very interesting to see how these things work. It's a field. It's a magnetic field that does that. And it's nice to see how it works. So when I think about slow fields, I like to think about that situation where they, right? We can also think about the birds flying to the forest that's not really dense, right? The trees are sporadic. It's not going to fly through the tree, right? It has to follow which way the trees are more separated, right? Or flying to the canyon or something like that, right? So the slope field will be this guide for our function to snake through. And you just, you take a step back and you look how the slope field looks like, right? What it looks like, and it will guide those functions. So let's take a look at the very cheap example, and then we can try spicier ones later. Say, I don't think they actually, let me see what they have in the homework. Let's say number 2 is fine. It says dy over dx is equal to x plus y. So there we go. Now, I don't really want to use what they have in a textbook. I want to generate this on my own completely. What do I know? I know that this dy dx is the slope. So I will call that m, slope m. I will assign to that slope m a value, say 0. So let m equal to 0. If m is, so this is what you pick. You choose the value. I choose 0 first. Then I will go with 1 and -1 and 2 and -2 and so on. So let me do the first one with m equals 0. When I plug that in the differential equation, I'm replacing dy dx by m equals 0. I get the equation 0 equals x plus y. And I can solve that equation for y equals -x. Now, I'm going to lightly circle these two and write here. I will place small 0 slope segments along y equals -x. This y equals -x is called the isocline. Isocline. So let's do this. I will start my graph here. The isocline is not important for my solution, but I need isocline as a construction line on which I will place the little line segments with slope 0. So I pick this gray color and I draw very light -45, right? So it's a -x, so it's this one. So this is a light gray line. It's isocline. And along this line in regular ink, I'm going to put horizontal 0 slope. Put them anywhere. But don't go crazy. Don't put too many. So what I'm doing here is, you can see each square and right. The more OCD you are, the better off you are for these kind of things. So here are the little guidelines for my. So now I can erase easily on the tablet. I can erase the isocline, which was the guideline. But I'm going to leave it. And I pointed with my with the arrow there that that line is the isocline. Now, what do? Let m be 1, in which case y1 is equal to x plus y is equal to negative x plus 1. So now I need to draw isocline, which is a linear line, negative x plus 1. Okay, I can graph basic things quickly. So it's going to be parallel to our previous line. But the little slopes on this one are slope 1, which is 45 degrees, right? Slanted 45 degrees. So I'm going to draw these perpendicular shapes now, like this. Because that's what a slope 1 is. It's perpendicular to the line. That's how it worked out. Do we all follow procedure? It's fairly simple. You pick a value for a slope, you plug in the differential equation, you get the equation for isocline, graph isocline, and then put those slopes along the isocline. Rinse and repeat for a different value. Let m equals to 2. 2 equals x plus y equals negative x plus 2. Yet another parallel line, the lines slope more. So they're no longer perpendicular. Now they curve more up. Well, I mean, they slant more up, not curve. So here is the isocline of negative x plus 2. So maybe I can put negative x plus 1, negative x plus 2, so we know which one is which. And now the slope 2, it's going to curve more, well, slope more. Let's see some negative numbers as well, right? Let m be negative 1. Negative 1 is equal to x plus y. So now y is equal to negative x minus 1. So negative x minus 1 is going to be, again, parallel to all of these lines. And we are looking for a slope of negative 1. Slope of negative 1, guys, was the slope of the isocline as well. So now these little line segments will be on top of the isocline. So isocline is a guide where you get to draw the little line segments with whatever the slope they have. So without spending now infinity of time here drawing 50 of these lines, do you all see, just for this little bit, that there is this general motion that it's happening? Stuff comes in this way and then goes like that. Do we see that that would happen? Right? Do you see how the field over here if you are to put a little pebble that can't go through these little holes, right? You would catch the slot and then just like go like that, right? Do we see that on this picture? That's what the slope fields do. Now, the slope field over here clearly gives us the general solution, because I don't know which one of these pink. Is this pink or magenta? People thought that there's magenta. I thought it was a person. Apparently it's a color. Yeah, I heard it from you.
I remember that.
So, how do I get particular solution? How do I get particular solution? This is going to give me infinity of general solution. How do I get particular solution? On what? Said that. That's it. What is initial condition? A point in space. You give me initial condition 2, 5. I'm going to put 2, 5 somewhere on the graph where 2, 5 is. There's going to be exactly one of these lines going to through 5, and the rest we erase. All right? So you see this one going, and that one goes through this point, and this point, and this point, and this point, and this point, right? And then this one over here goes through. There are infinitely many lines that are stacked between any of the ones I drew. This over here is all filled with these functions. That's what the plus C does, right? But only one of these will go through the initial condition, and initial condition is the point somewhere over here. So if I had to come up with a particular solution, right, then we have this. Now, once you draw the slope field and once you fit the function through the slope field, you can run regression, you can run whatever else to figure out what that function is. Remember, not every differential equation is solvable by separation of variables or whatever later we're going to learn. Bunch of them are solved numerically, some of them are solved this way. So to find the particular solution on this one, you will have to have initial condition, and that initial condition is as simple as a point somewhere, and the graph, one of the graphs, will actually end up going through it. That one is particular, everything else is general. Great? Nice. Now, observe what I said. Being careful, I said exactly one solution, one curve will go through that. Not possibly 2 or 3, 1. This goes now to a very important theorem, which is a theory of differential equations, on existence and uniqueness of solutions. Solution to differential equation exists, and then it's unique. Now, if you want to go back into the relatively many solutions, right, for the wave, sine wave that goes forever, yes?
Is the same theorem apply here, where you have like an n order equation for partial equations for many solutions?
Yes. Very good. We are going to see that you are getting one solution for the first order, 2 solutions that are linearly independent, but then they could be dependent and there was a way for us to fix it and so on. So yes, good. So we're going to have that. Cool. So I will write down the existence and uniqueness. Again, we will not be proving that theorem. The proof for, I know you're interested in that stuff. The proof for uniqueness is not difficult at all because simple contradiction. What you do is you assume that you are starting with 2 different solutions, and once you start plugging things in, it works out that it's the same. So you start under assumption that solution u of x and the solution v of x to the differential equations are two different functions. One is called u, one is called v. And then when you plug them together in the differential equation, you end up with u equal v at the end of the at the end of the calculation. So the proof is extremely easy. I would invite you guys to try and prove it and look into it if you're interested in mathematics, if you're a math major and so on. By the way, you all math majors for engineering? Do we have, who's engineering here? Hands high up, touch the ceiling. You all signed up for math major, right? Hands down if you're not math major. The hell? You gotta do that, guys. It's only 2 classes and a whole extra degree. So you have to take linear algebra and you have to take one more computer science class, whatever it is. So a full degree for $1,000 bucks. Come on, let's go. A full degree. So you will be transferring as engineering and mathematics. Also physics and mathematics. There we go. And then we have the physics, chemistry, and mathematics, triple. Physics, mathematics, and engineering. And right, so there we go. Triple majors are, it's not that crazy. I mean, you say to someone, whoa, they go crazy, but it's like 3, 5 classes.
Did you say that 2 extra classes for engineering and math were?
Linear algebra and whatever the, so you have a mandatory class in engineering and a mandatory class for whatever computer science. There are 2 computer science classes. One is mandatory for 1 degree, the other one is for the other. I know. Such is life.
For mathematics, you get a choice of 2.
But it's not the choice of the... Yeah. Because there's something, I don't know, whatever it is. The computer class, I think, for engineering is MATLAB, yeah, which is not for mathematics. For mathematics is the other.
Mathematics is
Java, yeah, and stuff. Yeah, exactly.
That was a fun class.
Yeah, no, they're not crazy. All right, so let's write this theorem down and sail into the night. Ready? So existence and uniqueness of solutions. Suppose that both the function and its partial derivative are continuous. So suppose that both f of x and its partial derivative dy of fxy are continuous on some rectangle R in xy plane that contains the point AB in its interior. Then, for some open interval I, containing the point A, the initial value problem dy dx is equal to f of xy with the initial condition y of a equals b, that's the point, has one and only one solution. That is defined on interval I. That's it. Can anyone tell me where is the core where existence and uniqueness hide in this mess of words? Like which verbiage, which part of the whole text here, from the beginning all the way to the end, which verbiage is the one that actually is existence and uniqueness with existence and uniqueness without using those words?
One and only one.
One and only one, yes. That's it. It has one, so exists, and only one. It's a unique. That's the verbiage. Very good. Very good. That's it. All right. So now you know how to generate slope fields. Now I will strongly encourage you to figure out in Mathematica, Wolfram Alpha, and so on the slope fields to generate, right? So you can check the homework assignment when you do it. And I'll be sending the link for Mathematica to install on your private machines this week. So it has to be tomorrow.
They run on Linux? Yeah.
I think that the version that we have is PC Mac only. I think, but it might be.
I got a laptop that won't run on Windows, so I gotta run it on Linux.
Yeah. Let me just say bye.